Okay, so today we're going over 2013 USNCO local exams from question 11 to 20. Sadly, I did something weird with screencast and I can't upload the 1 through 10 YouTube video, but I will link the screencast video in the description, assuming that this gets uploaded to YouTube. So please check that out. If you don't check it out though, basically a rundown of this series is that I'm going to go through some USNCO local exams to help you guys prepare. And basically, I'm going to answer 10 questions at a time and go through my thought process on them. Yeah, okay, so let's get started with number 11. We're looking at vapor pressure and temperature here, so the equation that should come to mind is the Clausius-Clapeyron equation. It's a little hard to pronounce. So that would be this. And since it's with regards to vaporization, we can put HVAP. So basically, we want a P versus T graph. So instead of having this natural log of a P ratio, we want to actually, find P by itself. And we can use natural log properties to say that ln of P2 is equal to ln of P1 and also you can make this a positive sign if you change this to T1 and this to T2, because essentially you're multiplying the parentheses by -1 and what's outside the parentheses by -1, so it cancels out. So if we continue this, we will have HVAP over RT1 minus HVAP over RT2. Okay, so if we're thinking of P1 and T1 as an anchor point, like we know what they are, and on the graph we're just varying P2 and T2, then we can consider this entire part, this entire chunk that relates to P1 and T1, our initial conditions, we can consider that a constant A. And the standard enthalpy of vaporization and R never change. They're not going to change no matter what we do to the pressure and the temperature, so that we can call a constant B. So if we look at this, and we can also drop the 2 because we're just calling these initial conditions now. We're going to say that ln P equals A minus B over T. Once again, we drop the 2 because we're only interested in this situation. If we make everything base E to eliminate the ln, then P equals E to the A minus B over T, and that's all in the superscript, that's all the power. I can make that more clear with the parentheses. So basically, let's look at what's happening here. If we increase T, then we're making the fraction B over T of less magnitude, so A minus B over T increases. And if you raise E to an increasing power, P is going to increase. That was a little bit of a mouthful, but hopefully you guys get the gist. So it should be an increasing trend, and all of these graphs do follow increasing trends. But we can eliminate C because we've got an E in here that's not linear at all. And we can eliminate D because it's got linear parts, it's got parts with slope equals 0. It's just weird, right? We want to see a nice smooth curve. So basically, we're looking at whether this is going to be exponential decay or growth, because that's the difference between A and B. A and B, the answer choices, not our variables. But one way we can discern that is, well, the reason that answer choice A is right is, like I said before, as T is increasing, A minus B over T is increasing, but that becomes especially true for larger values of T. So basically, you're going to increase the pressure more when E is being raised to larger and larger values. So it should follow a growth trend rather than a decay trend. So that's why we chose A for number 11. Okay, number 12. We ran an experiment, we ran a titration, and then we've got these concentration calculated. And basically it's a question asking what caused us to make this error. So we can just go through the answer choices. Some of the neutralized solution from trial 2 was left in the flask for trial 3. So that would mean we just have more volume in the flask, but we don't have more moles of the analyte. So if we have the same moles of the analyte, it's going to take the same moles and therefore the same volume of the titrant to titrate it. So we're not going to be using any more titrant. And, where is it? We measured the volume of base we're using, the analyte, we measure that beforehand, before we put it in the Erlenmeyer flask. So the fact that we have like water and like NaCl left over, adding volume, it does not matter because we didn't include that in our volume measurement. So this would have absolutely no effect on our concentration measurement. This would also have no effect because phenolphthalein is just the indicator, it's not participating in this reaction. HCl was used as 0.25 in the NaOH molarity calculation. It's kind of a stupid mistake to make. I mean, you guys can just do the calculations for yourself. You can confirm that it's wrong by just plugging the numbers in. But anyways, the reason why letter D is right is because if you spill a little NaOH, you're going to have less moles of it, but you already measured the volume, so your volume's going to remain the same in your mind, right? Because you won't know that you spilled any of it. But since you have less moles, that means it's going to take less volume of acid to neutralize it, and you'll think that you used less moles of acid, therefore. So a lesser mole value over the same volume value is a lesser concentration value, and that's why you would choose D. Okay, so if we look at 13, it's an ideal gas. Alright, so we can just use this. P1 V1 over T1 equals P2 V2 over T2. As long as you keep V in liters, P in ATMs, and T in Kelvin, there's really no way you can go wrong. So 0.5 times 298.15 times, oh wait, what am I doing? So ignore what I was saying. 0.5 times 1.2 over 298.15 is our like initial PV over T. P1 V1 over T1 is equal to about 2 over 1,000. And then if we multiply that by T2, which is 75 plus 273.15, we get 0.7, and then if we divide that by 3.6, we get 0.1946 liters, which is 0.195 liters. Basically, this is just from the various gas laws. Boyle's, Gay-Lussac, Charles. Yeah, I think that's all of them that are included in this. You also could have just done PV equals nRT, but you know, you're introducing stuff like N and R that do not need to be included. Number 14, you have a mixture of N2 and O2. You know the mole fraction, the total pressure. What is the partial pressure? The mole fraction of N2 is 0.7, and there's only N2 and O2. The mole fraction of O2's got to be 0.3. So 0.3 times the total pressure equals 0.426. 15. Which has the lowest boiling point? Okay, so basically we're going to be looking at intermolecular forces here, because if you have low amounts of intermolecular forces, or just weak ones in general, you're going to have a lower boiling point. So this has hydrogen bonding, because you have HL. This has hydrogen bonding. So cross those out. This one it does not have hydrogen bonding because the O is attached to the two C's, but it is, it's obviously not polar, but it will have more interesting interactions than A, and it is slightly heavier, I'm going to say, yeah, because this is 16, this is 12 plus 2, about 14. It's slightly heavier than A, and, you know, O is just more interesting. And it can do a lot more with intermolecular forces than this could. It's literally just propane. Okay, 16, which is correct about the critical point. Critical point, so on a phase diagram, triple point means that solid, liquid, and gas are all in equilibrium. It's where they all converge, and it's literally like, it looks like 3 different lines are coming out of the same point, so it's really easy to recognize. Triple point is when, if you go above that temperature, you can't distinguish from a liquid and a gas. Basically, their densities are going to be the same, and you don't know which is which, so you literally just call it critical vapor, I think. I'm not exactly sure what the term is, but they're indistinguishable, and that's what B describes. A describes a triple point. Liquid can be produced by changing pressure. Oh no, these are describing opposite situations, right? Yeah, so those would not be valid. 17. Equal volumes allowed to stand separate. Okay, so liquids will separate when their intermolecular forces are not similar to each other. So the reason why, let's think, the reason why like ethanol and water may not separate too much is because they both have dipole-dipole intermolecular forces, so they're very similar in that regard. So ethanol, methanol, they both have hydrogen bonding, so they're pretty similar. They're not going to separate too much. Hexane and pentane, it's pretty much just London forces here. They're not going to separate. And they're both alkanes too, so even if you didn't know that they, like, even if you didn't know what London forces were, you know, you could eliminate it like that. Carbon tetrachloride and hexane are both nonpolar. It's London forces at work again. This is nonpolar, like we covered here, but this has hydrogen bonding, so they are unlike, which is why B is our answer. For 18, same atoms at the lattice points, which lattice exhibits the lowest density? So if we draw like a unit cell, what would indicate low density is not having that many spheres in the cell. So simple cubic, if I remember correctly, it's literally just you have one sphere at each of the 8 vertices. So it would just be 1/8 times 8, so you would have 1 atom per unit cell. Body-centered cubic, it's the same thing, except you have this one dot in the very center of the cube, so you have 2 per unit cell. Face-centered cubic, you would have 4 per unit cell, I think, because you would have 1 at the center of every face, so 1/2 times 6 is 3, plus 1 is 4. Yeah, and then the hexagonal, oh boy, okay, I can't really remember what it looks like right now, but basically you can't get smaller than 1, right? Because it's got to be integers. So you know the answer is simple cubic. I'll look up the structure and I'll draw it in a future video. NaOH is added to water, temperature is monitored, determine the heat released. So I'll erase the ideal gas equation. Basically, we're going to have Q equals MCAT. You might have seen this written as this, but it means the same thing. I'm just going to use MCAT. So, our mass of solution is 110 grams because we're essentially assuming that NaOH becomes the solution too. C is 4.18. Oh, that's a little inaccurate. 4.184 is exact, but we'll just use what they tell us to use. And the temperature change is 14.2. There should be a negative sign on that because we are releasing heat, but as long as you know the magnitude, you're not going to get this wrong. So if you multiply hold on, I messed something up here. Oh, okay. Yeah, I see what I messed up. Don't be dumb like me. Please do subtraction correctly, and then you won't miss USNCO questions in a very stupid way. Yeah, so you get 11127.16, and that is this. Yeah, so a good lesson, subtract correctly. 20, which of these are equal to the heat of formation? So heat of formation is the enthalpy change when you create 1 mole of a compound from how its constituent elements are found in their natural form. So for example, that would be CS, that would be O2G, N2G, how they're found in nature. So if we look, both of these, there's 1 mole and 1 mole on the right, so nothing is disqualified yet. But if we look over here, that's not an element, so you can cross out anything that includes 2. But this works because they're elements in their natural state. It's 1 mole of product, and non-integer coefficients are not disqualifying because obviously if you're going to have n2 and you only have one n on this side, you have to multiply by 1/2. So that's why our answer is A. And that's the end of questions 11 through 20. Our next video will cover 21 through 30.